All right, stats. Here we are for your Monday, January 9th video, notes video, central limit theorem questions continued. You have just a few minutes ago received this here notes packet. All right, there's a little, very small, little handout, I guess we would call it. All right, anyway, call it what you want. It's notes. They're good questions. Let's have them out. Tuesday, we'll finish these notes. We'll have some more special questions on Wednesday. Thursday is going to be that in-class assignment, and your Chapter 11 homework set will be due on Friday, and then we will go from there, folks. All right, so let's zoom in a little bit. First, shout out to those sponsors. Number one, always brought to you by coffee. Coffee, nature's best vegetable juice. Next, brought to you by, yes, shout out to Southeast Missouri State University. You know, it's a school and it's close. So, two good things there. Okay, folks, number one. Take a look at number one. Random sample of size 10. Okay, so 10's not large enough. We don't know anything about the T distribution right now. All we know is about Z. 10 is not large enough unless you see these magical words from a population that is normally distributed with mean 12 and a standard deviation of 3. Find the probability that the sample mean is greater than 13. Okay, so first off, we don't know anything about X, guys. We can't define X. We don't know what it is. But we know X is normal with a mean of 12 and a standard deviation of 3. So that means X bar is normal. This is a sampling distribution. Mean 12 and standard error of 3 over root 10. 3 over root 10, which is not a great number. It's what, just under 1. So I want to know the probability that X bar greater, again, we always use equality there, greater than or equal to 13. So Z is X bar minus the mean over the standard error. Okay, so again, use your calculator well. Do the 13 minus 12 portion. Okay, let's get this. So here's what we're gonna do. I don't know if we're gonna be able to. Hey, now we're working. So you need to do what? 3 divided by root 10. Again, make sure you go to mode and make sure it's in classic, not math print. So 3 divided by root 10, you get that irrational number there. So immediately do 1 divided by second negative sign, second answer, and then I get 1.05. You guys know how to do that. That is much better than rounding and rounding again. Look up 1.05 on your Z table. You get 8531, I believe. The probability of being more than that is 1 minus 8539, 1, also known as the complement, 1469. All right. The width of washers produced in a factory has an unknown distribution. Uh-oh. We better see a certain sample size with a mean of 21 millimeters and a standard deviation of 1.1 millimeters. Sample 50, it's going to be big enough, is taken. Estimate the probability that the mean width is less than 20.75. So it's on the short side there. So X is the washer length. It's not a washer, it's the length. It's not the length, it's the width. What in the world? Who wrote this? All right, it's the width of the washers. All right. Anyway, it's probability that X bar less than or equal to 20.75. Z is 20.75 minus 21 over the standard error. Again, same thing. Figure out the numerator first. It's negative a quarter. Do 1.1 divided by the root 50. You'll get an answer, and immediately do negative 0.25 divided by answer. Negative 1.61 is that Z-score. Look it up. It's 0537, and that is the answer because it's less than. It's the cumulative probability up to that point. Cool. A second sample is all right, so this one is a little more involved. And we're going to need some space. So before you do this, write small, Put that curve up here, write a little small up there. A second sample is taken. The probability that the mean of this sample is less than that needs to be at most 1%. Okay, so again, this is on the small side, all right? So we Again, we're finding the sample size. We have yet to do, I think, a question like this before, so this is good. Again, why do I know? So I'm dealing with 1%. Why do I know it's the bottom 1% versus top? Because look at 20.75. 20.75 is less than the mean of 21, so we're going here. So I want a size so that the chance of this happening is 1% or less. Okay, so you want a bottom 1%, right? Z-score, so that's an area of 0.100, and if you look that up, that's negative 233. So negative 2.33 is equal to, so that is X bar. Normally we're searching for X bar, but no, they told you they want this, minus 21 over 1.1. It's still the standard deviation over the square root of n. Yeah, I don't know what this is. Whoa. Okay. You guys all have had to successfully taken Algebra 2 or Honors Algebra 2 with a certain grade, okay? So we can do some algebra. So negative a quarter, right? That's the numerator, right? So what did I do here? You're currently dividing by 1.1 over root n, so I'm going to multiply both sides by 1.1 over root n. That will cancel it here, so then I'm going to have a 1.1 over root n on the left side equals negative 0.25. All right, so I'm over here. Now I got to go to the other page. All right, so still, so what I do next? All right, so what I do next? I want root n all by itself. So when I'm right here, I'm going to now divide those sides by negative 2.33. A negative over negative is positive. Good. We're talking about sample size. We can't have any negatives in here. So this is now going to cancel. Now I'm going to be left with that, right? I'm going to be left with that, which is, it's roughly that, okay? All right. Wow. So continue. Okay, so I don't want root n in the denominator anymore, so I'm going to multiply both sides by root n. Root n's are going to cancel. Great. I want n by itself eventually, so I'm going to divide both sides by 0.107. That gives me 1.1 divided by 0.107 is roughly 10.28. Then we'll square both sides. All right. We're going to learn later, because it's set at most 1%. All right, so we're going to learn later in a different example that we round up, because it just makes sense to round up. But even if that was like 105.13, we would also round up. So sample size would be 106. We'll talk more about that in chapter 13 or 14. Pretty sure it's 14. All right, cool. It's 106. Wow, that was a pretty impressive question. Okay. So yeah, these aren't all like. This is from, I Googled Central Limit Theorem questions PDF, and whatever fine institution originally had these questions, I do thank you. So not all of them are Central Limit Theorem, okay? It might have been in a certain section. I think I might have looked for quiz questions too. This is not a central limit question, but it's a good question. So the random variable x has this probability distribution, all right? So it only takes on the values of 1, 2, not 4, or not 3, but 4, 5, and 6. So weird. So remember, this is everything. This is all the values of x. This is discrete because the values of x, you see no decimals here. So the probabilities need to be 1. All right, we'll maybe talk more about that notation, because you'll see that in higher level stats courses. Probability capital X equals little x. Anyway, so what's the probability of getting a 1? It's 0.1. Then we have k, 2k. We have 3, we have 2, 4. Anyway, we know that these need to add to 1. So this plus this plus this plus this plus this is 1. Got some more algebra. We're going to get 3k is 36, so k is 1, 2. So probability of that happening is 1, 2. Probability of that happening is 2, 4. Why do we need that? Because it wants to know the expected value of x. What's the expected value of x? Expected value of x is the sum of x times p of x. All right, so the expected value of x is 1 times that probability, plus 2 times that probability, plus 4 times that probability, plus 5 times that probability, plus 6 times that probability. So I would pause this, have that answer. That's a good question. Again, all of this is leading up. It's never too early to start looking at that final exam. All right. Okay, let's get back to the central limit theorem. The mass of duck eggs is normally distributed with a mean of 75 grams and a standard deviation of 6. Becky fills baskets with 24 randomly chosen eggs. 24 is not a big sample size, but you see normally distributed. X is the mass of a duck egg. Calculate the probability that the average, that's X bar, mass of a duck egg in a randomly chosen basket is less than 72. So that the mean mass, like in this basket, so it's a little weird because when it says in a randomly chosen, you think that they're choosing one, but they want to know what's the probability that the mean mass in this basket, because again, it says mean. So it's clearly an X bar question. If it said a randomly chosen egg in this basket of 24, that would be different. This could be worded differently. It should be like, given this basket, what's the probability that the mean is less than 72? Okay, we're going to use less than or equal to. So we want the probability X bar is less than or equal to. Z is 72 minus 75 over your standard error is 6 over root 24. So this is going to be a -3 up top. 6 divided by root 24, find that, type that in your calculator, then immediately do -3 divided by that answer. You get -2.45 as your Z score. Look that up, your Z table, 0071. So unlikely, 0.7% chance if you have 2 dozen in there. All right. Calculate the probability that the mean mass of these 24, again, of these 24, the mean mass is more than 76.5. So on the heavy side, Z, so there's my probability statement. Gotta write probability statements. Okay, I'm going to be really, focusing in on making sure that is there, making sure probability statements there are there and correct. Z is 76.5 minus 75 over standard error. 1.5 over this number, 1.22. The area associated with that Z score is straight 8s, 8, 8, 8, 8. 1 minus, because you're looking on the right side, 1 minus that is 11, 12. 11, 12. All right. Good question. Let's take a look at this last page, and we're going to look at some homework questions. I'm going to just give you a little bit of homework help because we should be working on that. Then, let's talk about eggs. All right, the weight of the eggs produced by a certain breed of hen is normally distributed with a mean 65 grams and a standard deviation of 7 grams. So X is the weight of a hen egg. Determine the probability that a single egg, that is X, chosen at random, weighs more than 72. We got a hefty egg here. Probability, oh shoot. All right, here's what we're gonna do. We're just gonna change this. Okay, this is now 75. Easy peasy. Yep, I did not read that right. So we're gonna change that to 75. Find the probability that is more than 75 grams. We get 2 as our Z score, because this is at random, no standard error. Your denominator is 5. I didn't even give you a sample size, so you couldn't do it any other way. 1 minus 97, 72 is 0228. All right, hopefully I read the next one correctly. This is a good question here. We had one of these with the traffic accidents on Friday. Treat a carton of 12 eggs as a simple random sample of size 12 from the population. What is the probability that the weight of the carton falls between those two? The weight of the carton. Guys, I can't do 750 minus 65 over this. You're going to get an insane Z score. And then you're going to get another insane Z score. And you're going to subtract them. And you're going to be like, 0. Yeah, so it doesn't make sense. You got to convert this into an X bar situation. Okay, so 750 divided by 12 means X bar, the mean would be 62.5 as the lower bound. 825 divided by 12, it's 68.75. So a little on the light side, a little on the heavier side. This makes much more sense now. You're going to have several questions where you have a total, but you got to divide it by 12 to put this in terms of find the probability that the mean is between those two values. Okay, here's the, I went out of order. Here's the z-score for the bigger side, right? Here's the z, or the, you know, larger result, above average result. Here's the z-score for the below average result. And I ran out of room, so I can give you the answer. But the answer is got to be 95-35, right? 95-35. So about guaranteed, you know, pretty much anything outside of that would be an outlier. Okay, so have that, pause it if you need to. That's another good question. Let's talk about this candy bar, folks. You don't want to advertise falsely the weight of your products. You know, so if you advertise something, if you make your product like too heavy, we're gonna cut down on profits, right? Like, you know, if you had a job somewhere and you always made the slushies or the milkshakes too heavy or overfilled, like your boss can be upset because it's not like you're selling those at a higher profit. You know, you're cutting in to profits. But if you sell something for underweight, then you've lied, and the public finds out, they're going to be pretty upset. People are going to stop coming. Profits sink too. Candy bar advertises its weight at 2.5 ounces. It is known that the mean is in fact 2.5 ounces, but it has a standard deviation, right, of 0.05. So there's some variability. In a random sample of 100 bars, what is the probability that the mean weight is within 0.01 ounces of the true mean? So they got to calibrate something, you know, because it's done by some sort of machine. We want to make sure the machine is working. So, Mr. X losing points. X equals the weight of the candy bar, which is dark chocolate. Buys it simple. All right. So X bar is normal with a mean of 2.5 and a standard error of 0.05 divided by root 100, because we have a sample of 100. Goodness. 0.05 divided by 10 is, just move the decimal over again. So you don't have to, guys, to be within 0.01 ounces means the difference between X bar and the mean is either 0.01 on the heavier side or negative 0.01 on the light side, okay? Because this is true. Like, you got to write a probability statement. To be within 0.01 of the mean is your 0.01 less and your 0.01 more. But you don't have to write then 251 minus 2.5 to get that, and 249 minus 2.5 to get that. Like, this is fine. I've already told you what the difference between the X bar and the mean is going to be. All right, so you get 2 and you get negative 2. What in the world? I'll tell you what. I'm going to take away my master's degree here if that happens again. All right, so same answer. Just got to switch those. Okay. So again, very high. Very, very high. So we know if it's off, if you have 100 bars in the and you get all the means, or if the mean weight is like 2.52 or 2.487, then something is off. It is not calibrated correctly. And a random sample of 50 bars, same sort of question. What's the probability? It's between these two numbers. Your standard error is going to be different, though. It's going to be a little higher, right? So 0.01 divided by some number. 0.01 divided by some number. So it's less likely. Less likely. Still very high. But with 50 bars, it is less likely. Okay, folks. So if you really want to make sure that this sucker, your machine is working, you want a large sample size. Okay? Large sample size. Because then you know if you get a result that's outside of that, then something is wrong with the machine. All right, so that's your notes video there. Great notes we had. Let's talk about your homework set. Homework set. All right, so I think you can do it all right now. I think you should at least get a rough draft in. So the weights of adult males are normally distributed with a mean of 172 pounds at a standard deviation. Obviously, it's going to be a lot of deviation, 29. So X is the weight of an adult male. Was the probability that one randomly chosen adult. Probability that X greater than or equal to 190. Okay, now you have a sampling distribution. X bar is normal. Same mean, you know how to find the standard error. 29 over root 25. Okay, you just did that in that notes bracket. This probability, now we have 40, so your standard error changes. Probability that X bar greater than or equal to 180, but you have a different standard error. Probability that X bar is less than or equal to 170, different standard error because you have a sample size of 100. Okay, so do number one. Again, you see probability statements. Have you define X. Hey, pregnancy. We did questions like that the other day. Lengths of pregnancies. That's changed though, but we're going to use it. Isn't it for us? Haven't we always? That's also changed too. Because it was for us, it was 266, 16. Let's say it's different. Let's say it's 268 and 15 now. What's the probability? One randomly chosen lady. One. Probability that X is blank. Now you have X bar. Probability that X bar at less than or equal to 260. 260 minus 268 over 15 divided by the square root of 40. You're going to do that sort of thing with C as well. And that sort of thing with D. 225 and 100 are nice numbers to use because their square roots are lovely. And we continue. Batteries. All right. A randomly selected one. So probability X greater than or equal to 63. And then it's X bar time with B, C, and D. All right, again, we're going to talk about more questions on Tuesday. What is the sampling distribution? Remember, X bar is normal, same mean, with a different standard error. Boom over root boom. You got to simplify that. You know, if you have, let's say, hypothetically, you had, 17 over root 64, you'd have to simplify that. Okay? So then you don't have to define anything. We don't know what X is. Then you'll find that probability. C, D, B, C, and D. You've been doing that the whole time here. Okay, reading speed. A randomly selected student. X is, reading speed of a second grader. Then you have a sample of 30. Chevy Cobalt. All right. A randomly selected Cobalt gets greater than or equal to 30. X is the miles per gallon of a Cobalt. 40 are chosen, 25 are chosen. X bar time. Hey, we know about the IQ scores, test scores. This is all X bar. All right, folks, that is your homework set. This has been a lovely help video. Zach Math Video signing out.